simplify the indefinite integral of 3x plus 1 over x to the 4 plus x squared. We're going to jump right in and set up a partial fraction decomposition. The first thing we do is we want to factor the denominator. I can see an x squared factor can come out of both, and that'll leave me with x squared plus 1. Can we factor this further? No, this is actually probably the most basic example of an irreducible quadratic. If you don't believe me, of course, you can bust out the quadratic formula and check that discriminant b squared minus 4ac, but since the b term is 0, the minus 4ac stuff is going to leave you with a negative number under that square root sign. It has no real roots. If it was x squared minus 1, yeah, we could factor and get a couple more linear terms, but it's an irreducible quadratic. How is that going to affect things for us? So set up our decomposition. So 3x plus 1, x to the 4 plus x squared. So first we'll deal with that repeated linear factor, a over x plus b over x squared. And then for the irreducible quadratic, I like setting up a cx plus d over x squared plus 1. I do know other people like setting up individual fractions here. X squared plus 1 gets a cx, and then it gets another d. It's just a question of whether or not you want it as a combined fraction or not. I like it as a single fraction. And that's just me, but people who really like, integrating with building block formulas and things like that, they might want them separate for that eventual work. But I like it because that way each factor gets its own fraction or partial fraction, whereas if you split it up, then suddenly all your irreducibles get a cx and they get a d, and so it's doubling things, but some people don't mind with that. Okay, so we've got to find constants a, b, c, and d that make this work. What's the best way to do that? I find usually the first thing to do is get rid of the fractions, multiply both sides by x to the 4 plus x squared, which again, remember the bottom here factors as x squared times x squared plus 1. So you multiply this side by that. That's just going to get rid of the denominator. You'll be left with 3x plus 1. Okay. Multiply x squared times x squared plus 1 by a over x. One of the x factors will cancel out, and you'll be left with a x squared plus 1. Same thing with b, except you'll cancel out both x squared factors. And finally, the cx plus d here, you'll be canceling out the factor of x squared plus 1, and you'll just be left with x squareds here. Okay. So what can we do? Well, if we just had distinct linear factors, one common approach is to identify where those linear factors are going to be equal to 0, and because we've got polynomial on the left, polynomial on the right, just evaluate both at such a spot. And it helps you isolate things. For example, I know if x is 0, then this term and this term are irrelevant because they're going to be equal to 0. So if we say, well, let's let x equal 0, on the left-hand side, you'll have 3 times 0 plus 1. And on the right, all you really have is b times 0 squared plus 1. So that's going to tell us 1 is equal to b times 1, so 1 is equal to b. Well, that's great. That's pretty handy for us. Okay. What else can we do? So I'm just going to update this. We've got 3x squared plus 1 is a, x times x squared plus 1. b is 1, so I'm just going to go ahead and completely substitute that in. So we'll have x squared plus 1, and then we'll have cx plus d times x squared here. I guess I don't really need those brackets. Okay. Now with irreducible quadratics, there's nothing I can do to make x squared plus 1 equal to 0, not with real numbers anyway. So I can't start isolating for c and d that way. One thing we can do, we can cancel out the plus 1s on both sides, and I can actually bring the x squared over here. But usually in such a situation, I like multiplying everything out. So ax times x squared is ax cubed plus another ax. And we already brought this x squared over to the other side. And then cx times x squared, that's going to be cx cubed plus d times x squared. Okay, so why would I do this? Well, one thing about polynomials is, if we collect like terms here, coefficients in two equal polynomials are equal. There is no way you can get one polynomial that has completely different coefficients to another polynomial and have them always be equal. Sure, they might have some intersections, but to have them be equal for every value of x, it doesn't work unless all the coefficients are equal. Okay? So we collect like terms. We have a single x squared term, a single x cubed term, a single a term. Okay? And comparing those things, we can see, oh, 3 and a must be the same. Well, that's pretty easy. D and -1 have to be the same. And a plus c x cubed has to be, well, there aren't any x cubes over here. There are 0 x cubes. So that's also telling me, a plus c is equal to 0. But I already know a is 3. So we can see, oh, c is going to be -3. So this gives me my partial fraction decomposition. A is 3, b is 1, and c is 3, and d is -1. Or sorry, c is -3. So actually, I guess we could take out a factor of -1 here. And write this as 3x plus d. Right, that should be fine. Or 3x plus 1. It's kind of interesting. We got the 3's and the x's here, and the 3's and the 1's, and we got 3's and the 1's here. I wonder if there's a good reason or if that's just coincidental. Probably isn't. There's probably a reason. But we're now in a position where we can finish this off. Okay. So we'll rewrite this. So we got 3 over x plus 1 over x squared minus 3x plus 1 over x squared plus 1. Okay. And now, so the question is, well, how do we want to deal with things? In particular, how do we want to deal with the irreducible quadratic? We can go the long way around and try and do a substitution, or we can remember, we can split it up and apply some of the building blocks that we've learned, building block number 3 and building block number 4 in particular. Okay. So we get 3 over x dx plus 1 over x squared dx. I'm going to split this up. I'm going to say minus 3 over minus 3 times x over x squared plus 1. Okay. Minus, don't forget our dx, 1 over x squared plus 1. Now, it's really easy to do that. We don't even need a formula for this portion here. This just goes straight to arctan. Okay. This one up here turns into 3 ln x, so let's not forget our absolute values. Plus, this turns into -1 over x squared, so we'll get rid of, change our sign here. And then now in the middle, what's going on here? And this is where you might use, you can do some rewriting, or you could do some substitution and things like that. Or if you just remember a building block number 4, which teaches you how to deal with x over an irreducible quadratic, you can do, so what is it? You have to know the a, b, and c of your irreducible quadratics, in this case 1, 0, and 1. And so you'll get 1 over 2a ln of your irreducible quadratic. And then it's minus b, which is 0 over, well, hold on, if it's 0 over the whole thing, then it'll be 0 over a, square root of whatever, but that's just going to be 0, so we actually don't even need that. We're lucky in that way, too. Okay? And as I say, if you're not a building block sort of person, you could take out a factor of 2 here and introduce a factor of 2 here, and then suddenly the top is the denominator of the bottom. Right? So you can definitely do that, too. There's lots of ways, and then very quickly you do a substitution. You got u on the bottom, du up on top, and you're all set. Okay? But this one's actually pretty nice and quick. We can just simplify this. So 3 ln absolute value of x minus 1 over x minus 3 ln absolute value, 3 over 2, sorry. 3 over 2, 3 halves ln absolute value of x squared plus 1. And then it was minus arctan x. And we do not forget our plus c. I'll just make sure I copied that all over correctly. Looks good. We're all done.